Okay, so cylindrical coordinates was not a big jump because we were experts in polar and we were experts in triple integrals, rectangular coordinates, and it was just kind of putting those two things together and putting a polar system into our three-dimensional system. So that was pretty straightforward. The spherical coordinate system is a whole new animal. It's like, this is totally different. So spherical coordinates. So there is one thing that carries over, one thing we're familiar with, and that's that theta. So one of the coordinates in spherical coordinates is theta, and it's the same theta we've used for trigonometry and for the polar coordinates and for the cylindrical coordinates. It is the angle swept counterclockwise from the positive x-axis. So I'm showing it with this gray half plane, right? And we saw that in cylindrical coordinates, that theta is represented by like a half plane now. Okay? So theta is the same. And so the range of theta is from 0 to 2 pi. So in polar coordinates and in trig, we allow for angles, negative angles, angles greater than 2 pi. But normally in cylindrical and spherical coordinates, we just constrict theta from 0 to 2 pi. Okay, so then the next coordinate is a new angle. Okay, so the new angle is phi. And phi so given an angle theta, so it's kind of like we pick theta first, okay? So we pick theta, so I'll pick theta something like pi over 4. So theta is about pi over 4 there, okay? Once that angle theta is picked, then phi is the angle in the theta half plane, the measure tipped down from the positive z-axis. So watch, this is what, sorry, what was I saying? Did I say phi? I meant phi. Phi is the angle then tipped down in the theta plane from the positive z-axis. So here is phi equals 0. Phi equals 0 represents then the positive z-axis. Phi of pi over 4 would be tipped halfway down to the xy plane in the theta plane. So theta is determining the direction that we tip down for phi. Does that make sense? Okay, and then what would phi equals pi over 2 be? What would that represent? XY plane, in the XY plane, something like that. And then what's the maximum value of phi? Pi, which would be negative z-axis. Now we consider all that in whatever the theta direction is. So if I have, here's theta equals pi, right? Back in the negative x direction. So then phi is, can't really see that too well. Let's turn it a little bit. Does the blue still show up? Okay. So then this is what theta is negative pi. Sorry, theta is pi, right? This is the negative x-axis. And so then phi is 0, pi over 2, pi in the direction of theta. So if I'll just hold phi at about pi over 4 there, and then change theta now. So this is for a constant phi, changing theta. So phi is, the range of phi is 0 to pi. And again, what is, we ought to define this. Phi is the measure of the angle tipped down from positive z-axis in the plane, the half plane of theta. So theta determines the direction or the where we tip down for our angle to get our angle phi. And then the last thing is also a new coordinate or a new quantity, and that's rho. And rho then is distance from the origin. In the direction determined by both theta and phi. So now I could set theta equal to pi over 4, like that, and set phi to 3 pi over 4, so that's like tip down like this. And then rho of 0 is what? Origin. And then say here's rho of 1 unit in that direction determined by those two angles, rho of 2, etc. So then rho is how far you are from the origin. I'll say, so just to get a feel for these three things. So again, so we know theta is like theta equals 2 pi over 3. What would that be? Phi equals, say, 3 pi over 4. And rho equals 2. So what set of points, what would the set of points be if we had a constant theta, say theta of 2 pi over 3? What does that give us? Yeah, that's like the half plane. Somewhere around there. A little bit further maybe. So that's something of the angle or the half plane for theta equals 2 pi over 3, what I'm showing there. Okay, what about phi equals 3 pi over 4? For all points, phi 3 pi over 4. So for all rho and for all theta, but hold phi constant at 3 pi over 4, what would we get? Can you imagine what you would get? So it's every point in all directions if you're tipped down 3 pi over 4. So something like this. So can you imagine that blue line? What set of points would that blue line sweep out? So think of all rows now. So all rows. So think of this whole blue line as a varying row. So some people are seeing it. It's sweeping out a cone, right? A cone, right? So this is, this is a half plane. This is a cone. Opens which direction? Opens down, right? So this opens down on the negative z-axis. So again, imagine that blue. So imagine that blue line, not just the point at the end, but the whole blue line sweeping out points. Do you see that would sweep out a cone? Okay, if phi was pi over 2, it would sweep out the plane, it wouldn't be a cone. But any other value but pi over 2 gives you a cone. Except phi was pi over 2, then it sweeps out the xy plane. Okay, what about rho equals 2? So for all theta and phi, what would you get? Sphere. Thus, this is the reason it's called Spherical coordinates, because a sphere is the easiest thing to define. Rho equals 10 is the sphere with radius 10 centered at the origin. Right? Because it's all points that are 10 away from the origin. So this is a totally new way to think about defining points in R3. Questions so far? Okay, so let's look at some relationships here. We've got lots. Now we have X, Y, Z, R, theta, rho, and phi. And these are all, and we want to be able to transfer between these different systems. So we have to have all the relationships. And that's no small task. So let's look at, I'm just going to do a generic theta here. Okay. All right, that's pretty good. Okay, so right away we know that this is rho right here, right? Okay, and then I can drop a perpendicular to the xy plane. Right there. And what would that quantity be? Or what variable is that right there for this point? So this is our point right here, ultimate, so that's rho. What would that be? Yikes, guys, what's the distance from the point to the xy plane? Z, right? That's Z. Right? Okay? And then I'm going to finish that triangle like this right here. And what's that dimension right there? Thank you for saving us. R, right? Things we know from before. Okay? And then I want to take this one back here to the x-axis. And what is that? Some of you are saying it. That's y. That's the y coordinate, right? And then this right here would be x. Let's get our right angles here. This is a right angle, right? Which one is a right angle in this vertical triangle? Exhibit A, B, or C? C is a right angle. Okay, can you see where angle theta is? First of all, is theta in the horizontal triangle or the vertical triangle? Horizontal. And you should be thinking that it's this angle here. That's our theta. Right? Okay, and can you imagine where is the angle phi? Between rho and the z-axis, right? So this is our phi right here. And so then where else is it? Yeah, so this is parallel to this right here. These are parallel. So this is in our triangle. This is also phi. Do you see that? Are we good so far? So can you imagine what we're talking about here? So let's start with R. R is equal to two different things. So R is the kind of it's in both triangles, right? It's in the horizontal triangle in the xy plane. It's also in our vertical triangle with rho and phi. So what is R? Okay, so we know from before that's the square root of x squared plus y squared. And now it's something new. Okay, but we're going to define rho in terms of the other ones instead of that way. Would it be cosine for phi? It's opposite the side. It's opposite of phi, right? It's opposite of phi, so it will be sine of phi. Hypotenuse is rho, right? So it'd be rho sine phi. Is everybody tracking here? Hypotenuse is rho, right? Z and R are the legs. So R would be rho sine phi. What's that? Nope, rho is the hypotenuse, right? Z and R are the legs because this is our right angle. So R and Z are the legs, so rho is, this is the hypotenuse. This is going to be rho sine phi, or in other words, R over rho is sine phi, opposite over hypotenuse. So R is rho sine phi. Okay, and what is X? What we know from before? X is R cosine theta. But what's R? It's going to be R, right? R times cosine theta. So Y is rho sine phi is R sine theta. Z is now what is it? Rho cosine phi. So Z is now the other leg, the leg adjacent to phi, right? Z is the leg adjacent to phi, so it's going to be rho cosine phi. Okay, remember what theta is? So, arctan of, okay, adjusted to be the angle that we want, right? Arctan gives you an angle between negative pi over 2 and pi over 2. Maybe that's not the angle that you want, so you have to adjust, right? So you have to be aware that the range of arctangent is an angle between negative pi over 2 and pi over 2. But theta goes from 0 to 2 pi, right? I think you discovered that in your homework. Was there some in your homework like that? So hopefully, if you didn't work that out and you need help, then get help on that, because that's trig. But you got to get that settled. Okay, so now what about, so any questions so far? So R is kind of our bridge between polar and spherical, right? R is involved in both because it's involved both in all these polar relationships, and now it's involved in these spherical relationships because it's involved with Z and rho and phi also. Good so far? Okay, so now let's talk about defining rho. So come over here. So what is, I made it blue, so let's make it blue. So how does rho, yes, let's do rho squared. So rho squared would equal R squared plus Z squared. And what is R squared? What's R squared? X squared plus Y squared. So rho squared is? And that should make perfect sense. Why does that make perfect sense? This is our equation of a sphere, and we know that so rho is the radius of a sphere centered at the origin, right? This is our equation of a sphere. X squared plus Y squared plus Z squared equals radius squared. So that works. Okay, what is phi? So now so if we're going to define phi, we want to think about, Let's choose wisely here. What do we say the range of phi is? From what to what? 0 to pi. So if we want to use either arcsine, arccosine, or arctangent, which one would make the most sense? You guys know what the range of those three are? So there's arcsine, arccosine, and arctangent. Remember what the range of each is in terms of the angles? Sine is from negative pi over 2 to pi over 2, because we need all y coordinates, right? If you think about the unit circle, we're doing arcsine. Our input is like a y coordinate, right? So for all y coordinates, we want to get all possible angles. So then that range is negative pi over 2 to pi over 2. So is arctangent, like we talked about. And what about arccosines? It's kind of like given all x coordinates. The range is, if you remember from arccosine, 0 to pi. So if the range of phi is 0 to pi, then it makes sense to use which of these three? Arccosine. So we want to write phi in terms of arccosine because then we're going to get the right range of angles, right? When z is negative, we're going to get those angles between pi over 2 and pi, that's exactly what we want, right? When phi has gone past pi over 2 and z is negative, that's like x being negative in for standard trig, right? And that's going to give us those angles greater than pi over 2, less than pi. So arccosine of what? Arccosine of z over rho. Good. And then in rectangular coordinates, that would be arccosine of z is z over rho, which would be square root of x squared plus y squared plus z squared. So that would be if you had rectangular coordinates and you wanted phi. Okay, so just watch out for blindly just using these, like plugging in the formulas to get the answer that you need. You've got it. Make sure you're thinking about what the angles and the distances mean. Okay, think about that and draw pictures. Don't just blindly plug into the formulas. As we know, here's one trap that you fall into with arctangent, right? You got to know the geometry of it in order to get those right. Okay. Okay, questions on the relationships between x, y, z, r, theta, and rho and phi? Okay, so now we got to talk about, if we're doing spherical coordinates, what is dv, right? So if we're going to do a spherical triple integral over some solid E, we're going to have some function of rho, phi, theta. The question is, what is dv? We saw that when angles come into this, it's not just going to be d phi, d theta, d rho. Why? Because phi and theta are not distances, right? They're not distances. They're angle measures. So we know, as we've seen before, this is not going to just be simply d rho, d phi, d theta, or whatever. Okay? It's going to be something else. So let's try to figure out what that something else is. So I think I'm going to start again. I'm going to erase this and start again. No, I'm going to go for it. I'll do it. So now I've saved red, so I'll do everything in red from here. All right, so we're going to figure out what dv is. So what is dv? It's a little element of volume based on a small change in rho, a small change in theta, a small change in phi. Okay, so can we draw that? Let me try to draw that here. So it's kind of like, here's our change in, so this side of it would be change in what? What's that to change in? phi, right? That's the change in phi, that dimension there. And then say this dimension here. Let me draw the whole thing. I need to do this in a different place to make the picture better. So I'm going to erase this and start over. Any questions on what I've written up there? Are we good? Okay, I need to tip this down more. That's going to be better. Okay. So okay, so that's the dimension. So that's going to be our, so here's, this is phi. And this is theta. And so then, change in theta would be like this. Okay, that's pretty decent. Okay, so this is our little dv element. So this here is based on what? This is rho. Right there, that's d, not d rho. D phi, right? This is like changing the angle phi a little bit. Okay? So what is this dimension right here? It's not, d phi is not a distance, right? So that's the amount of change in angle. So how do we get that little change in distance? Right there. Rho d phi, right? So it's the radius times our, our circular arc length is the radius times the angle measure, right? So that right there is rho d phi. That should make sense, right? Because it's the radius times the angle, the little change in the angle. Okay, what is this dimension right here? How about this one right here? Do it up here. So that one right there. That's d rho. That's going a little bit out from the origin, right? That dimension right there is our d rho. So this one here is rho d phi, the radius, or the distance out, times the angle measure, is the arc length, right? And then d phi, sorry, that's to here. That's to here. That dimension right there. And then finally we've got this one back here. What is that? So that's based on the change in theta. That's like rotating back around into the screen that way. So that's like a little change in theta. Right, so that's our d theta. And so then what is that dimension? Right? What is that length? If this is based on the change in sweeping a little bit of theta, what was that again? Yep, r d theta, right? Because this is r. That was the same thing we had in polar, right? So one dimension is simply d rho, that's just a little change away from the origin. And this one is going to be rho d phi, the radius times the change in the angle. And this will be r d theta, again, the radius times the change in that angle. Do you see it? So what is dv then? dv equals rho times r times, and the order will normally d rho, d phi, that will be normally the order that we integrate in. D rho, d phi, d theta. Okay, but we know r is not a spherical coordinate, so what is r in spherical coordinates? Rho sine phi. That's what we did earlier. So we have our dv is rho squared sine phi d rho d phi d theta. So this is analogous to when we came up with what? R dr d theta. We got these extra terms in there that's turning those little change in angle into actual little distances, right? So this dimension, rho d phi, this dimension back here, r d theta, and then d rho. So then, what will this be? So how will what will our mantra be? First, we'll go from inside to out. So it's like the archer is now standing in the origin. He's going to shoot out from the origin and see where it goes in and leaves the surface. Okay, so how far away, what rho equals what? Like what radius away does it enter and then leave the solid? Okay, then phi is going to be, so what's our starting, we tip down from the positive z-axis, so it's going to be the starting phi to the ending phi, as thinking of phi tipping down from the z-axis in the direction of theta, and then starting theta to ending theta. What's that? So theta is the same angle, so it's the starting theta will be the one that's starting closest to the positive x-axis, and then rotating counterclockwise. Same theta as before. That's the one common element here that we have with spherical coordinates is theta. Okay, did I lose you? Please ask if I lost you with any of this. Please.
The order of DP integral would be from when you're shooting an arrow from the origin.
Mm-hmm. Yeah, so you'll start thinking about the archer will be standing on the origin, shooting out away from the origin. So it'll be what? Closest surface to furthest surface of the solid. Like where does it pierce in and where does it leave? It's closest to the origin and furthest away. Okay, so a real easy example, so how about E for say a bottom half sphere. So the bottom half sphere with radius 7. So what would write the limits of integration. So we'd have this integral, right? Some function, and we have rho squared sine phi d rho d phi d theta. So write the limits of integration that would get the bottom hemisphere that has radius 7. So rho would go from, Trevor, what do you think? Rho would go from what? 0 to 7, right? Because the solid goes all the way to the origin. So the starting place is 0, and then the ending place is 7. And then phi would go from pi over 2 to pi. Because you'd be starting at the xy plane. That would be exactly pi over 2 tipped down, and then you'd be tipping all the way down to the negative z-axis. And then theta would go from 0 to 2 pi. So those, if you were integrating over the bottom half sphere with radius 7, those would be your spherical coordinates, or so your spherical limits. And you'd have whatever function, you'd have to get that function in terms of rho, phi, and theta, and then the rho squared sine phi multiplies times the function, just like r did before, right? Questions on that one? All right, now slightly harder example. Set up the integral and spherical coordinates to find the volume of the solid that's defined as between these two surfaces in the third and fourth octants. Do you remember what the third and fourth octants are? It's just like the third and fourth quadrants above the xy plane, right? So the first four octants are just like the four quadrants for positive z. So see if you can do that. So you're doing the same as what we just did here, but now for this. Okay, you done? Let's see. Austin, how'd this go? What'd you get for rho? Rho from what to what?
I got rho from
6 to 9. So they're saying something different. So that's actually what, isn't that? That's would be like rho squared, right? In our spherical equation. So it would be square root of 6 to 3. Do you see that? Okay. And then phi. Go ahead. Okay. She wants 0 to pi over 2. Yep, 0 to pi over 2. That's right. And then theta. Lauren, did you get theta? What was it? Pi to 2 pi would get us in the third and fourth. Pi to 2 pi. So what would that be? That would be like a band shell, right? It'd be like kind of like a band shell. Opening this way, right? I don't want to try to draw it. But you can imagine like a hollow sphere, right? And like 1/4 of it over here. All right, I'll try. Better than I thought it would turn out. All right, question, yeah.
Because it says in the third and fourth octants,
Mhm.
does that imply that it would be above the xy plane?
Yes, that's what I was saying originally. So yeah, first octant is the one we deal with the most. Second, third, fourth, and then you go below the xy plane, you get 5, 6, 7, 8. Yeah, are all under z, negative z. Okay, so now harder one. Questions? Yeah. Oh.
I'm just wondering if you can figure out that.
I'd have to give it to you. So yeah, so f would just be, if it's given to you in x, y, and z, then you have to use those relationships to change it into rho, phi, and theta. Does that make sense? So x, yeah, you have to change it because you're integrating with respect to rho, phi, and theta. So that function has to be in terms of rho, phi, and theta. So every x would be just what? Rho, sine, phi, cosine, theta. You just use those relationships and plug things in. But look for, before doing that, look for, see, do I actually have that? Yeah, here you go. So here, so you're going to set the integral and spherical coordinates. Here's the function f this time. So I'm actually giving you a function f. That's f of x, y, z. But you want to set this up in spherical coordinates. So you're going to integrate f over this solid. Inside x squared plus y squared equals 4. Below z equals 5. And outside of x squared plus y squared plus z squared equals 4. I should say above. How about above? Let's say above. There you go. So get a really good picture. Make sure you got a good picture. This is harder. This is more. There's more. It's more complicated. Think about it. Apply the things we. Okay, what's going on with this problem? Okay, Archer stands at the origin and fires. Where does the arrow enter the solid? Rho equals 2. Where does the arrow leave the solid? Where does the arrow leave the solid? Enters at rho equals 2. Leaves at z equals 5. Okay. Anything else? What about when phi is greater? We have a greater value of phi. Enters the solid at rho equals 2. Leaves the solid at r equals 2. Yeah, so z is, what is z? Rho cosine phi? So rho is, someone said 5 over cosine phi, is that right? So here rho depends on phi, right? It's not constant rho. It depends on what phi is, and it's actually 5 secant phi, right? 5 cosine phi. But then over here, what is r? Rho sine phi. So rho equals 2 over sine phi. So where the arrow leaves the solid depends on what? Depends on phi or theta? Phi, right? There's this dividing line. There's this angle phi right here, where for all angles of phi less than that phi, this is a key phi right here, phi, so I call it phi 1. All angles less than phi 1, the arrow leaves the solid through what? 5 over cosine phi. For all angles phi greater than phi 1, the arrow leaves the solid 2 over sine phi. Therefore, we're going to add triple integrals. To be continued. So it's just like before. So now different angles of phi are going to give us different exit points from the solid for our row.